Okay, so let's start today's lecture in our course of modern physics. Last time we started the study of the wave-like properties of matter particles. So I want to remember a few things we saw. First, the de Broglie. Boa tarde, Jurman. Eu estava começando a gravar a aula porque, como eu não gravei a da semana passada, então é bom porque você vai estar acompanhando. Tudo bem com você?
Tudo. Boa tarde.
Boa tarde. Ok, então eu comecei a lembrar o que a gente fez na semana passada para começar o que a gente vai fazer hoje. Tudo bem? Vamos lá. Sorry, Okay, so we saw the last time the de Broglie hypothesis. De Broglie said that matter particles also could have wave behavior, and so he wrote two relationships. Okay, the first one relating the frequency with the frequency of the wave with the energy of the particle, okay, and they are related through the Planck constant h, and the second one relating the wavelength of the wave and the linear momentum of the particle, also related through the Planck particle, and the relation is this one, okay? And so I also told that when I can, I will use this notation lambda dB for de Broglie to remember that it is a wave associated with a matter particle. Okay, so we also have this one for the photon. Okay, the energy of the photon, which is a particle, is hf, and the linear momentum is h over lambda, and this lambda is not lambda de Broglie because this lambda is really the wavelength of the wave. Okay, so we saw the experimental demonstration of the pertinence of this description, made by Davis and Germer. And so Davis and Germer, they made the experiment with electronic waves, okay? The control, so this is, you have an electron beam and it is diffracted by a crystal. And so you observe at some angles, depending on the kinetic energy of the electrons, you detect maxima of diffraction. And if you calculate using the Bragg condition what would be the wavelength associated with such a diffraction, you find, for example, in this case for electron with 54 electron volts, okay, would correspond to a wavelength, a de Broglie wavelength of 1.65 angstrom, and the calculation using the de Broglie expression is 1.67, so very close. And so we finished last lecture with these experimental demonstrations. This one is from J.P. Thompson. Okay, so today today I want to go on this subject, and this is what we are going to see today. This is the problem of the wave packets. So we studied the properties, how we can associate a wave to a material particle. But actually, when we have a wave, an electromagnetic wave, or a wave in a string, or in water, on etc. Mechanical waves, as I here. So we know what is waving. We know what is oscillating. For example, in water, you have or sound, also sound wave. So we can describe it through the oscillation. For example, for the sound waves, the oscillations of some air. You have to have some material medium. So the sound can propagate. So these are pressure waves. And so on. In the case of the electromagnetic wave, we know that electric magnetic fields oscillate, and when we describe the wave, we write it as a function, of the electric field oscillating or the magnetic field, and both are related through some relationships. But in the case of the matter wave, we quite artificially decided to associate a wave to a material particle. And so the question is, what is waving? And so some aspect we have to emphasize here. In the case of a matter wave, you don't have the need for a propagation medium. For it to happen, you have a particle propagating in moving in the vacuum, for example, and there is no ether, and we know that it is you can associate a wave to it. And also the other problem is that the particle is localized. When we describe an electron as a particle, we usually do it saying that it has some position in the space and some velocity, some acceleration, and things like that, but particularly it has some position x, y, z in 3 dimensions. And so I will study 1D classical wave, to show you that you can have some localized wave even in 1 dimension, or in 2 dimension, or in 3. So classical waves, if you remember, classical waves, they are the solutions of a classical wave equation. So in 1 dimension, this wave equation relates the spatial variation of the wave. I called it psi here, so it can be the electric field or the magnetic field of an electromagnetic wave. It can be some movement in a string, something like that. So this is spatial, and this is temporal. So you have a relationship between the spatial variation and the temporal one, and the coefficient between the two of them is 1 over v squared, where v is the velocity of propagation of the wave. Here I choose z as the direction of propagation of the wave, and sometimes I will switch to x, so maybe be careful, because here I call it z and sometimes I call it x. So psi is the oscillating quantity, and the z and v, the direction and velocity of propagation of the wave. And so you have this equation, and you find some solutions of this classical wave equation. And a very known one, a very useful one, is the harmonic monochromatic wave. Okay, so this solution can be written this way. You have that psi of the position and the time is some amplitude, psi naught, and some spatio-temporal variation. Okay, this is a phase kz minus omega t. Okay, and you have the cosine of this phase, and we can write it. So here we have as a function of z and t through k and omega. So k is the wave number, omega is the angular frequency, and we can also write it as a function of the wavelength, lambda, and the temporal period. Okay, lambda is the spatial period. Okay, so psi naught is the amplitude. So what is the unit of psi naught? This is the oscillating quantities unit. So if it's an electric field, this will be the unit of an electric field, volt per meter. If it's spatial or in a string, this will be meters and things so on. Okay, so you know it very well, and so this solution, for example, here I have drawn them here as a function of space. Okay, you have here psi over psi naught. Okay, so this is normalized. Okay, from 1 to -1, and so on. And here the x-axis is also normalized by the wavelength. So you have here the wavelength, which is lambda, and so z over lambda here you have one wavelength from 0 to 1, 2. Okay, and so the same thing here as a function of time, psi over psi naught. Okay, and the time is normalized by the temporal period t. Okay, and so you have this behavior you know very well, and what you can see here, and it's that this harmonic wave is spatially and temporally non-localized. Okay, so you cannot say, particularly here in the spatial description of the wave, you cannot say, for example, you have here at this position z equal 2 times the wavelength. Okay, z over lambda is equal to 2. Okay, it seems difficult to associate the position of a particle to this kind of behavior. So actually, what we have is that a solution of the classical wave equation can be any linear combination of solutions. Okay, so you can make some combinations of harmonic waves. And so, for example, you probably have already studied the propagation of a pulse in a string. Okay, so you don't have an harmonic wave. Okay, so this is a triangle. Okay, shape for the pulse, and it is propagating along the string. And this is a solution of the wave equation. It is not a harmonic wave, and it is spatially and temporally localized. Okay, so at each time you know where the pulse is. Okay, and so what we are going to study today is what is called a wave packet. Okay, so a wave packet is a superposition of harmonic waves with different amplitudes and frequencies. Okay, and wavelength. Okay, so this is actually a wave packet. So it has to be constructed so as to result in this shape. Okay, and here we have shown some very simple, okay, sum of a few harmonic waves, and we still are in the classical waves. Okay, so for example, if you have the superposition of two waves, okay, k1, k2, okay, this is the wave number, angular frequency, omega 1, omega 2, frequency, wavelength, propagation velocity, okay? So you write the superposition of these two waves as the sum of the two waves, y1 and y2, okay? And so you write it, these are two harmonic waves, and so this is the first one plus the second one. And here, to simplify, I will use the same amplitudes for the two waves, okay, to have a simple expression for the sum, okay? So I said this is y naught, and so when you have, okay, here I remember this formula, cos theta plus cos phi is a function of the cosine of theta plus phi times cosine of theta minus phi, okay, over 2, and you have this factor 2 here. And so this is what we have, okay? We have 2 y naught, okay, cosine of the sum, okay, and here cosine of the difference. And we can write it as the product between two cosines. Here we have k bar, which is k bar is the medium, okay, of the two wave numbers, k1 and k2. Same thing for omega bar, and here we have delta k, which is the difference, okay? And so you remember probably from your lectures on classical mechanics that what you obtain is some bit, okay? And so you have here drawn the two waves here, y1 and y2, okay, they have the same amplitude and they have some dephasing. And here we observe the bit, okay, of these two, the resulting, okay. So for example, I don't know, yes, here you have the result. You see that here, well, it's not very obvious to see because it's very small and very, but here you have one, the two at this point, they are exactly in opposition. This one is maximum and this one is minimum. So at this position here, x, okay, this is the position, you will have a node, okay? The amplitude will be 0, okay? And so the same thing here, you have 0, and here you have the two of them, they are maximum at the same position. So here you have a maximum, okay? And so you observe this envelope, okay, of smaller, okay, of this is a bigger frequency, okay, and so this higher frequency is related to the, I can write it here, okay, you have the product of two functions here, cosine, okay, let me take it, okay, this is what is important here, okay. And so, what is the higher frequency? You have each one, okay, k here. Oh, well, in relation to the, okay, the spatial frequency here because it's spatial. So you have k, okay, bar, which is equal to half k1 plus k2, okay, and you have delta k, which is equal to 1 minus the other. Let me see here. This is k1 minus k2. Okay? And so, you see the order of magnitude of this wave number will be the same as k1 or k2. It will be only between, okay, the two of them. So, this is of the order of k1, 2, okay? And this one, this is the difference. As these two wave numbers are quite similar here, okay? So this will be much smaller than, okay, any of them, okay? And so this is the small wave number, okay? Small wave number means a higher wavelength, okay? And so the higher wavelength will be this one, okay? You have a higher wavelength, and here you have the smaller wavelength, okay, which is associated to, so this is associated to K, okay, and this is associated to, the envelope is associated to delta K, okay? And so we introduce here two quantities, okay? The phase velocity. The phase velocity, you already know it from each wave has its phase velocity. This is omega over k. So for the pitch here, we have omega bar over k bar, okay? So this phase velocity will be the velocity of this rapidly varying, okay, oscillations, okay, inside, okay, so this one, okay, they pass through this envelope at the velocity Vp, which is the phase velocity, and Vg will be the group velocity, okay, this will be velocity associated with this envelope, okay, and so this is delta omega, okay, associated with this term here, delta omega over delta k. Okay, and so here you see that you begin to see only with two waves, you have the beginning of localization. Okay, so you can say you have a wave localized here, here. So it's not completely localized. Okay, but here it was completely delocalized, and so only by summing two waves you have localization, okay, starting. And so by increasing the number, okay, I just summed two waves, okay, but if you increase the number of different monochromatic waves, okay, the localization of groups increases. So this is a group, okay, and it will increase. And here we have an example in the book. Okay, this is a tippler. Okay, so you have here, this is a frequency, this is another one. Well, the frequency seems quite... And so you have some amplitudes, okay? And the function of the amplitude is this one, okay? So instead of having all the waves with the same amplitude, you engineer, okay, these waves, okay, so that they will result in this kind of, okay, wave packets, okay? So you see that here we have 15, I think these are 15, yes, 15 harmonic waves, okay, with this particularity. This is the function, this is the why not, okay? So each wave, they don't have all the same amplitude. You see this one is smaller, okay, it's increasing here, it's diminishing here. So what is the function here? So you have here, let me write it. This is the amplitude y of k, okay? So it is not all the same. It depends. And so this is this way, okay? You have an envelope, okay? And so if you increase the number of waves, you can increase the localization of the wave, okay? And so if you sum an infinite number of harmonic waves, you can obtain localization, okay? So this is a wave packet, okay? This is a wave packet. And so it is not exactly at one position. We will see that it is really a fact, okay, that you have some kind of uncertainty on the localization, okay, of the wave, but it is quite localized. And so here we can, depending on how you can call this one, for example, this distance between the two nodes, you can call it delta x, for example. And here you have the function. Okay, so your wave packet psi of the position and the time, okay, is an integral. Okay, you have an infinite number of waves of a. This is the amplitude. It depends on the wave number. Okay, you are summing, okay, on the wave number, and you have this harmonic function. Okay, until now we used cosine, but obviously cosine, sine, and exponential. Okay, they are harmonic waves. Okay, so you have some delta x, and here you have some delta k. We will come back to it soon. Okay, so in this case you have the phase velocity. Okay, the phase velocity is the frequency times the wavelength. Okay, so you have, this is omega over k. Okay, so this is the phase velocity for, regardlessly, you can have a phase velocity for each of the waves, but you will have something around k bar. Okay, k here. Okay, so this is where you will calculate the phase velocity. Okay, for this average, this central, okay, value of k. And you have the group velocity. Okay, so the group velocity describe the propagation of this wave packet. Okay, so you have the group velocity here. You have here, I can write it in Vp. Okay, phase velocity, group velocity, and so you can write it as T omega over Tk. Okay, and so as you have omega with this function of Vp, okay, they are proportional through k, and so you will have that the group velocity will be Vp, okay, plus, so you derive T omega will be k Tvp, okay, plus dk Vp, okay, and so you have here over dk, and you obtain that the group velocity is the phase velocity plus this expression here. And so to have the velocity, the group velocity different from the phase velocity, okay, it is when this term is non-zero, okay, so when the phase velocity depends on k, okay, and in this case we call it dispersion, okay, a dispersive medium is where this happens. For example, if you have light in vacuum, okay, you have an electromagnetic wave propagating in vacuum, so the phase velocity is the product of the frequency times the wavelength, okay, always, and it is equal to the velocity of propagation of electromagnetic waves in the vacuum, which is c. Okay, c is a constant, you know it, okay, and so in this case it's only c. Okay, you don't have this dependency on the wave number, so you have the group velocity equal to the phase velocity. If you propagate light, okay, inside a dispersive medium, okay, so I don't know if any of you has studied, for example, propagation of electromagnetic waves in fibers, okay, optical fibers, and so the material of the fiber, this is glass or some special glass, and so there are dispersive media, okay, and so you have this effect of dispersion, okay, when you propagate an electromagnetic wave in a waveguide, okay, optical waveguide, and so you have the group velocity different from the phase velocity, and so you have this is described through the index of refraction, okay, n, which is the ratio between the velocity in vacuum to the velocity in the medium for this k, okay, this is Vp of k. Okay, so I think you know it. Okay, so let us go on with this description of classical waves. Okay, this is very useful because you probably already know a lot about classical waves, and you will see that these properties we are seeing, okay, we will find them again, okay, for quantum, okay, waves, okay. And so we have here the classical uncertainty relations, okay. So you can characterize when you have a wave packet, okay. The wave packet has some kind of localization, so you can call here d delta z, which is a characteristic width of the wave packet, okay, and here a characteristic width of the wave number, okay, of this is the around the central wave number, okay, when you build your wave packets, okay, so you have some number, okay, and some width of wave number around this k, okay. So typically you have from k bar, okay, medium, minus delta k over 2 eventually, okay, 2 k bar plus delta k over 2, okay. And we can show, I won't show it for in the general case, it is not obvious, but typically you have this relation between the width, the spatial width, and the k width, okay, and it is on the order of unity, okay, and the exact value here depends on, okay, the way you are building your wave packet, okay, but I can show you something that probably you already know. This is very used, for example, in circuits, okay, so you have when you speak about bandwidth and things like that in electronic circuits, okay. So what you have is here, you have the sum, okay, the sum on only two harmonic waves, okay. And so I remember you here the expression of the sum, okay, when they have the same amplitude. And so you have this envelope, okay, these wave packets, okay, which are related to delta k, okay, while I didn't draw them, but you have here the fastest, okay, varying, which are related to this one, okay. So we are not very interested here in what is inside the wave packet, okay. And so we can call here delta z, okay, the distance between two nodes, okay, here. And where do you have these nodes? It is when this, when this term here, okay, is 0, okay. So you write for here, for example, cos delta k over 2 z, okay. We are not very interested in the phase. Let's say that we are t equal to 0, okay. So you have cosine delta k over 2 z, and this is equal to 0, and this means that delta k, this phase here, is equal to pi over 2 plus an integer number of pi, okay, q equal to 0, 1, 2, okay. And so you can have, this is ZQ, okay, ZQ, you isolate it. So it's 2 pi over 2 delta K plus Q. This is a integer, this is a quantum number, okay. And if you write the next one for Q plus 1, okay, you will have the same expression here plus Q plus 1. And so this would be, okay, this is, for example, this is ZQ and this is ZQ plus 1. So delta Z is the distance between the two nodes, okay? And so you show that delta Z is equal to pi over delta K, okay? 2 pi over, no, sorry, this will cancel, and this is 2 pi over delta K. And so you have this product, delta Z times delta K, equal to 2 pi, okay? So this is a very specific case, but you see this is 2 pi, because it's a few units, okay? And so we have this relation between the width of the spatial and the wave number, okay, width of the wave packet, and this is some number, okay. And so this means that if you have a number here, which is some kind of constant, okay, if you increase, okay, the width of the wave packet, okay, delta Z, you will have to decrease, okay, the number of the width, okay, of the wave number, okay, around K bar, okay. And so now that I have shown, okay, this is called uncertainty relations, okay, because you have each one of them is some kind of uncertainty. For example, delta Z, okay, this is some uncertainty on the positions, okay. So if you say that this is a particle, okay, and so it is somewhere here, okay. And so let's go back to our material particles, okay. Back to particles wave packets, okay. The nature, so what is waving, okay? What is the nature of our wave? It's not an electromagnetic wave, it's not a mechanical wave, okay? This is a wave function, okay? And so what we are going to describe here, this is through a wave function. So from now on, okay, next time we will study the Schrödinger equations. And so in the same way that an electromagnetic wave, for example, the electric field of an electromagnetic wave obey the wave equation, which is for electromagnetic wave. This is the Maxwell wave equation, okay? So we will have the Schrödinger equation, okay, which will describe the behavior of the wave function, okay? So the wave function is psi, it is a function of the position and time. Here, this is a one dimension, okay, wave function. And so what we know, this is this one, okay? And what we know, it is the starting of all this history, okay, with the Breuil. So we have this relation between the wave and the particle through h, okay, the wave and the particle through h, f related to the energy, and lambda related to the linear momentum, okay. And so if you take a free particle, okay, for example, an electron, okay, you have free electrons, and so you can write that the wave function of this electron is a harmonic wave, okay. So you can write it as a cosine function of a sine function of a superposition of cosine plus sine. And so if this is very convenient and this is very useful to use the exponential, okay. So you know that exponential of I, you have the phase here, so okay, z. Okay, here I'm using z minus omega t. Okay, so this is cosine, okay, of kz minus omega t plus I sine of kc minus omega t. Okay, so let me put it someplace. Okay, so this is some way. Okay, so this is complex wave. Okay, and so I guess we are going to use a lot. Okay, this complex formalism because it is really very useful. Okay, so the phase velocity in this case, okay, you have the phase velocity, which is the product of the frequency and the wavelength. And so you can write it as a function of, okay, what we know. So F is E over H, and lambda is P over H. And so you have that the phase velocity is the energy over the linear momentum. Okay, so these are three. Okay, this is particle, this is we would like it to be, okay, obviously if we are going to associate this wave, okay, this wave here to this particle of energy and E and linear momentum P, we would very much like to have this velocity being the phase velocity. Okay, and if we write here the classical energy of a free particle, okay, so classical energy, this will be non-relativistic. Okay, so we are really, the kinetic energy is half the mass times the velocity square. Okay, and there is no potential energy here because this is a free particle. Okay, so there is no potential energy, and we can write it as p squared over 2m, where m is the mass of the particle. And so you put it here in this expression, so you have Vp equal E over pi, or over p, sorry, and so this is p over 2m, and so p over 2m, this is v over 2, okay? And so you have this factor 2 between the phase velocity and the velocity of the particle, okay? So this is the phase velocity of the wave, and this is the velocity of the particle, okay? So what we see here, okay, to summarize here, a harmonic wave, I used it to describe a free electron, for example, okay? You have no localization, okay? You have an harmonic wave, so you can see you have it extends from minus infinity to plus infinity, okay? You have no localization of particles, so it is not very physical, okay, to describe a particle. And so you have delta z, which is infinity, okay? It's infinite because the particle can be anywhere, okay, along the z-axis, okay, between minus infinity and plus infinity. And so you have a very well-defined lambda, okay, and a very well-defined f, so a very well-defined wave number, and so the uncertainty on the value of k is 0, okay? And also, so this is, okay, not very nice. And also you have that the phase velocity is different from, of the wave associated to the particle, is different from the velocity of propagation. So you correct these problems, okay? You solve these problems by describing your particle by a wave packet, okay? So what I did about wave packet before was for a classical, okay, wave packet, okay, the way you know it. And now I will use it for a particle, okay? I will build a wave packet to describe the behavior, okay, of the particle. Okay, so what I want, okay, if I have a wave packet, so I have localization, okay, because you have a finite uncertainty on the position, okay, you have a finite width, okay, of the distribution of wave number around k bar, okay. And so what about the group velocity, okay? Because we don't speak anymore on phase velocity because we have a wave packet, so we have to speak about group velocity, and this is okay. So let's do it. We have the group velocity is the derivative of the angular frequency in relation to the wave number. So we write again, okay, what we know. We have this relation between the energy HF, okay, this is from De Broglie relations. And so H, I can write it as H bar, okay, time omega. So we will use, depends, sometimes we will use HF and sometimes H bar omega. Same thing for P, okay, P is h over lambda, and we can write it as h bar times k, okay. So the linear momentum, okay, of my particle, okay, can be related to the wave, okay, through h bar k, and h bar, I remember you, this is the Planck constant over 2 pi, okay. And so we write the group velocity, okay, of the wave packet, and this is d omega over dk, and so omega is e over h bar, dE over h bar, and dk is p over h bar, p over h bar. So you write it and you find that this is dE over dp, and this is v, okay, because E is equal to p squared over 2m, okay. Okay, so you have dE over dp is equal d over dp of p squared over 2m, okay. So this is 2p, okay, over 2m, okay. So this is p over m is v, okay. This is the propagation, the velocity of propagation of the particle, okay. So wave packet, particle, they have the same value, okay. Okay, so this is nice. And so now that we have something, okay, we are building something more physical, okay, to describe a wave associated to a particle, okay, it is beginning to make sense, okay. And so now we would like to know exactly how are we going to make this previsions, for example, how are we going to use it to describe the particle, okay, in its wave-like behavior, okay. So what we can see is that the amplitude of this wave function, okay, I remember you, this is the wave function. So this amplitude at any position and time, okay, is related to the probability of finding the particle at that position, at that time, okay. If you look at this wave, okay, can be, no, this one is not a very nice wave packet, okay. This is a nice wave packet, okay. So you have this intuition that when you describe the particle with this wave packet, and the particle is not here, and the particle is not here. It is somewhere in between, okay? This is inside, okay, this wave packet. And so we have this notion, okay, that the amplitude is related. Okay, when I say amplitude, it is because here you have the amplitude is 0, okay, and this is maximum. And so probably, okay, we will have something like, or we have highest higher probability of finding the particle at this position than at this one, okay? So it can be here, but it's probabilistically, it is more probable that the particle spends more time here than here, okay? And this is the probabilistic interpretation, okay? The probabilistic interpretation of the wave function, okay? So what is it? What is it? It is the modulus, the square modulus of the wave function, okay, which is proportional to the probability of detecting the particle in a unique length, okay. So to remember you, this wave function can be complex, okay. So at the end, when we want to describe some real particle, and this is what we want to do in physics, okay, and you have to have real, okay, values. And so when you have the modulus of the wave function, okay, this is real, okay. So psi is complex, but modulus of psi square is real, okay. So we can do some physics with this one, and this is we can do physics for this one also, but to have some values, okay, some quantities, real quantities, they have to be real, okay. So this is proportional to the probability of detecting the particle in a unique length here, because this is one-dimensional, okay. If you have a psi, if you have 3 dimension, okay, you have psi of r, the position, okay, which is x, y, z, and the time, okay, time d, I will put here some volume, okay, so this is the probability of finding the particle, okay, inside volume. At position r, okay. So you have some x, y, z, and you have some elements of volume here, and you have here the position, okay. So what is the probability to find the particle in this volume, okay, here at this position r? So this is the modulus, the square modulus of the wave function times this volume. In one dimension, this is the square modulus times dz, okay? This is the probability of finding the particle between z and z plus dz, okay? So this is the interpretation of the wave function. Why do we say this is probabilistic? It is because you see here, I think you have the particle can be here or any place inside, okay, this wave packet. And so we have, when we are going to make measurements, for example, you have some identical electrons, okay, they have the same wave function, okay, and so if you make a measurement on, for example, the position of these electrons, so even though they have the same wave function, if you make a measurement, you can find, you won't find them all at the same position, okay? And so some of them you will find here, and some of them they will be here, and some of them here, okay? But if you do a lot of measurements, okay, obviously you will find a distribution, okay, which will have this shape here, square, obviously, okay? And so you will have much more, you will find really much more electrons here than here, okay? But you will find them, okay, in all, okay, the wave packet, okay? And so I think that's it, okay? So coming back to the uncertainty principle, okay, so I began with the wave packet, the classical wave packet, the classical uncertainty principle, and now I saw the this is a quantum wave packet, okay, the wave function and its interpretation, the probabilistic interpretation, and here the uncertainty principle, which is Heisenberg, okay. So you have your wave packet. So I'm using X here because this book here, I think this is the brand. Okay. To take this figures, okay. So you have your wave packet here as a function of X, and you have here the distribution of wave numbers, okay, of all the waves forming, contributing to this wave packet. So psi of X, you integrate from minus infinity to plus infinity. Actually, you see that minus infinity, you don't have a lot of, and plus infinity also, it will be very small, okay? A will be very 10 to 0, okay? So you have something which is quite localized in this space, K space, okay? And so this is this amplitude, and this is, we used to call it cosine, okay, of K at X, okay? And here this is exponential, this is the complex notation, okay? So you sum, okay, you sum over decay, okay? So you have a lot, okay, an infinity of waves, okay? So we saw that for classical waves we had this uncertainty, okay, classical uncertainty principle, okay, between the width, the spatial, and the wave number width, okay. And also, okay, I didn't speak a lot about it, but you have kx minus omega t, okay, some function, okay, so cosine, sine, exponential, okay, and so you have this uncertainty relations, okay, delta k, delta x, and here you also have delta omega, delta t, okay. Okay, you find the same relations, obviously. And so when we treat now of matter waves, and so we have this relation, okay, I repeat them. So you can write that delta P, okay, you want to, when we are using, for example, for an electron, okay, you are going to describe the wave function, okay, you won't use, you will use more the linear momentum, okay, than the K, okay, so the linear momentum is associated with the particle, okay, linear momentum of the electron, the energy of the electron, and so delta P, okay, will be equal to H delta K, delta E will be equal to H bar delta omega, and so if you write delta X delta K, you will have delta X, delta K will be P over H bar, okay, so you have the uncertainty on the position times the uncertainty on the linear momentum, they are on the order of H bar, okay, and same for the energy and the time, okay, and so this is the uncertainty principle, okay, Heisenberg, and it means that we are going to see here, okay, it has some implications, okay, it means that if you want to know with a great precision, okay, what the position of your particle is, it means that you want this delta x to be very small. So you necessarily will have to increase, okay, the uncertainty on the measurement of your linear momentum, on your velocity, okay, and this is the contrary if you want to have a great knowledge of the linear momentum, okay, you will lose some knowledge on the position of your particle, okay? And so one of the implications of this uncertainty principle, okay, this is the minimum energy of a particle in a box. A particle in a box, it means that you have some particle, okay, confined, okay, in some part of the space, okay. So, for example, here, let's see for we will have some examples here. For example, a macroscopic particle in a box, okay, and here an electron in an atomic box, okay. So, for example, you have an electron, you have your hydrogen electron atom, sorry, okay. So it is very useful. We already saw how Bohr described, okay, the first quantized, okay, the first quantized description of the atom, okay, with discrete energy levels and things like that. So you have one electron, okay, and you have one proton, okay. And so we already saw some wave-like behavior of this electron around the proton, okay, when we saw that this how Bohr quantized, okay, Bohr quantized the angular momentum, but this is equivalent to have a wave, okay, confined in a circular, in a ring, okay, on a ring. So in order to have some constructive interference, okay, you have this confined wave, okay, has to repeat itself, okay, after one round, okay. And so this is exactly the same thing as you probably studied, okay, in classical mechanics, okay. You have a string, okay, and so you will have the string confined, okay, between two extremities, okay, here. So this is L, and you have the modes, okay, of vibration. You have this one, and so on, okay. But here we are interested in the energy of this particle in the box, okay. So here you have some confined wave, okay, a wave confined in a one-dimensional box of length L, okay. So the particle is in the box, okay. You put your particle in this box, so you know that it is here. So when you calculate, for example, okay, psi of x, okay, square, okay, this is different from 0, okay. So if you integrate between 0 and L, okay, this one, so this will be equal to, what is the probability of finding, okay, this is the probability of finding your particle, okay, at position x, okay, in the an element of length t dx, okay. So if you integrate this between 0 and L, you will find the particle, okay, because you will look for it at all the positions, and so this is equal to 1, okay. So this is very important. We are going to use it a lot, okay. And so as your particle is in the box, so you can say that the uncertainty on this its position is smaller than L, okay. Maybe you don't know where it is exactly, but you know that it is inside the box, okay. And so as you have delta x, delta p on the order of h bar, okay, so the uncertainty on the the linear momentum will be higher, okay, than h bar of L, okay. So we can, to describe, okay, to measure this delta p, we can use the standard deviation, okay, as a measure of this width, And so we write it here, sorry. Delta P square, okay. If this is the standard deviation, you know that the definition is, this is the value, okay, minus the average value, okay, the mean value, okay. And so actually you will do the sum of it and divide by the number of, okay. So this is the average of this quantity squared, okay. And so you write it this way: p square minus p bar square minus, sorry, plus minus 2p p bar, and you are looking for the average of this one. So this will be the average of the sum will be the sum of the average, and so you will have p square average, okay, plus p average, p mean, okay, square, minus 2 blah blah blah. So at the end you have this expression, okay. So this is very important. This is p square average minus p average square, okay. These are two very different quantities, okay. Particularly if you have a symmetric box, you will have p, the mean p will be equal to 0, because p is proportional to the velocity, and the velocity, if you have a symmetric box, you will have the particle, okay, going this way or this way, okay. So this will be perfectly symmetric, and so the velocity, okay, v, will be equal to 0, okay. Sometimes it is to the right, sometimes it is to the left, okay. In average, it will be 0, so p bar is equal to 0. So your measure of the width, okay, of the linear momentum square will be, this is 0, but p square won't be equal to 0, because if you can have a mean velocity equal to 0, but when you do it square, so they all have, okay, let's say you have some velocities this way, okay, so you sum, you will have 0, but if you square it, this one will be, okay, everything will be positive, and you will only sum, okay, this contribution. So the average, the mean of p square is different, is not 0, okay. And so this quantity here will be larger than h bar square over L square, okay, h bar over L. And so what are we looking for? We are looking for an expression of the energy, okay. So we have this energy, which will be the minimum of energy, will be proportional to this mean value of p square over 2m, and so it will be larger than this quantity h bar square over 2m L square, okay. And so you cannot have a wave packet, okay, a particle with 0 mean kinetic energy, okay, in a box, okay. A quantum particle, okay, always will have a minimum energy, which is called the 0-point energy, okay. And here it depends on the dimension of the box. Obviously, you see, if you have a very large box, okay, you are going to, for example, free space, okay, you have no box, so you let this length go to infinity, okay, and so this minimum energy goes to 0, okay. But if you have a box with finite dimension L, you will have finite value of the 0-point energy, okay. And so to finish here, let's do 2 examples, okay. A macroscopic particle in a box. So to calculate, why don't we know that already, okay? I have studied classical mechanics, never heard of that. And so let's consider a small but macroscopic particle of mass 10 to the minus 6 grams. Okay, this is very light particle, okay, but if you compare it with an electron, for example, what is the mass of an electron? M is on the order of 10 to the minus 30, okay? Sorry, kilograms, okay? So 10 to the minus 27 grams, okay? So here we have 10 to the minus 6, so it seems very small, but it's still macroscopic. And let's say it's confined to a one-dimensional box, okay, with L equal 1 micrometer, okay, 10 to the minus 6 meter. For example, a tiny, tiny bed on a very short wire, okay? So you have this bed here, and you have a very short wire here, and the bed can, okay, explore, okay, all this wire, okay? And so we want to know what is the minimum kinetic energy and what is the corresponding speed, okay, corresponding to the minimum energy. So we use, okay, the expression here, and if you do that, you will find that this is a very, very small energy, okay, 10 to the minus 48 joule, and even if you write it in electron volts, 10 to the minus 29 electron volts. So this is really very, very small, okay? And if you calculate the velocity corresponding to this one, you will find that it is of the order of 10 to the minus 19 meter per second. So this is why we won't observe it for macroscopic particles, okay? Now, if you study an electron in an atomic box, okay, the electron is confined, okay, in the potential attraction, okay, in the potential energy, actually, of the, for example, in the hydrogen atom, you have your proton, okay, so you have a positive charge, a negative charge, and you have Coulomb attraction at some distance, and if you come closer, okay, you will have a repulsion, and because of okay, this is no more Coulomb. Okay, Coulomb is 1 over r, okay, the distance, so this is attractive, and so your electron, okay, it's like the moon, okay, around the earth, okay, it is confined, okay, in the potential energy of the earth, okay, and so you can say this is a particle in a box, okay, in a 3D box, and here we are studying an electron in a one-dimensional box, and this box has dimension L equal 1/10 of a nanometer, okay, this is about the diameter of an atom, okay, 0.1 nanometer, this is 1 angstrom, okay, and this is an electron, this particle. What will be its 0-point energy? We calculate with the same expression. Here I used the value I had found here, okay, in joule, 5.56, 10 to the minus 48, and I only changed the mass, okay, and the length, okay, so this is the old length, the new length, the old mass, the new mass, okay, and so I find that this energy is 6.1, 10 to the minus 19 joule, okay, so this is a few electron volts, and this is actually the right of the order of magnitude of the kinetic energy of an electron, okay, in an atomic box, okay, so an electron confined, okay, around the nucleus of an atom, okay, and so to finish this lecture today about the wave-particle duality, and so essentially what we have to say that you have waves, waves behave actually you have some object, okay? You have some physical object. Behaving as wave, okay, and also as a particle, okay. And so we have seen it for light, okay, electromagnetic waves, okay. So you have the quantities associated with this wave are the frequency, the angular frequency, the wavelength, okay, and so on. And they also behave, you have here the photon, okay. Photon has an energy, it has a linear momentum, okay. And you have okay, and you have particles, okay, material particle. What is the difference between a photon and material particle? Okay, so essentially the photon has no mass. Okay, the mass of the photon is 0. In the vacuum, the photon has a velocity which is equal to c. Okay, a material particle. Okay, it can be an electron. Okay, which is really some elementary particle, but you can also speak of. Sometimes you can describe an atom, okay, and so the atom has some structure, okay, is constituted of electrons, of protons, okay, and it has quarks and things like that, okay, and so a material particle which has some energy, some linear momentum, okay, also behave as a wave, okay, matter wave. Right here, matter wave. With wavelength, double wavelength, etc. And so this wave behavior, okay, you will describe it through diffraction and interference experiments, and the particle behavior, collisions, etc. Okay, so for example, when we show that photons, okay, the light also can be described as particles, okay, this was Compton, for example, okay, Compton collision, okay, and so this is to close this subject.